All right, cool. So, hi, I'm Wayne. For those who don't know me, I'm the other section's GSI. And those who do know me, yeah, you better know me. So, all right. So today we're going to talk about informal analyses of experiments. And this is actually pretty important. So far, we've been teaching you box models, experimental design, whatnot. And this is just another example, all right? And like when we talk about when you do an experiment, what do you need to think about? What should you think about? What should you ask? How do you prepare? Things like that. So let me first prep you up. The first thing we're going to talk about are babies. How early do they start walking? And what kind of training program do you give them? Okay? So it's just you on your own. What would you do if you wanted to test? You had a method. You believe, okay, this method will definitely make babies walk earlier. Okay? How would you test it out? How would you run an experiment like that? So let me say one way. If I was like, hey, I'll just grab a bunch of babies and give them the special training I came up with, and let's just compare them to everyone else who did not sign up for my program. Okay, so I just put a billboard out, Evans Hall. Be like, people who have babies, come to me. And for those who don't, I'll find my other colleagues who didn't join my program and just look at their babies and just test their walking rates. Why is that not such a good idea? So I just posted something on the board, be like, people who want to join my program, join. People who don't want to, I'll just go find you after. Allison. Such as? Can you be more concrete about what are these things that might be influencing? Maybe you have a super baby. All right, cool. Andrew?
Babies who aren't in your program might be in like another one or like some other kind of trying to teach them to walk a different way.
Okay, so Andrew said maybe the parents are trying to teach babies to walk a different way. So the parents were actively seeking these things, right? They want to train their baby earlier on. They want them to get the best education and whatnot. This is a very special group, right? You can't tease apart the effects of the parents, of them being active teachers, versus the parents who are like, my baby will just learn on their own. I'll just let them grow on their own, okay? So you need to do an experiment. But how will we do an experiment? So this is a bias, right? This is a bias that we need to get rid of. And you all know that, okay, how do we get rid of bias in experiments? Randomization, right? What do I randomize? How do I randomize? This is hard, don't worry. And this is why experimental design is hard, okay? And you'll be stuck with it forever. And this is why it's so beautiful. All right, so the goal of this study, what they did is they grabbed a bunch of babies, 20 babies for this instance, and each baby was randomly assigned one of the 4 training programs. So although I do want to just train my special program of walking exercises, there's actually also a regular exercise and a no exercise, but I just have a weekly follow-up. So every week I go and just check on your baby. Is your baby walking yet? Is your baby walking yet? And the other one is no exercise, no follow-up until the very end of the program. So at the very end of the program, I go and be like, did your baby start walking or not? And what week did they start walking? Okay? So they're, in a sense, what's my response, what's my conditions, and what are my units? Okay? So when you see these things, you have to start thinking, what's the next slide? What's the next slide? What's the professor going to ask me? Okay? That turns out to be that. So what are my 3 key elements? Nick? Well, what are we interested in? What makes someone a better walker? If they walk earlier, right? So that's the time. So Nick said that the units are the babies that we're performing the experiments on. The conditions are the 4 treatments that we're going to give them, right? The only one visit, weekly visit, regular exercise versus special exercise. And then the response, when you're ever stuck with one thing, just ask, what is this thing supposed to do and whatnot? And so the response, what we're interested in is how early our baby is walking, Okay, so that's just the time when your baby starts walking. That could be in terms of days, in terms of weeks, probably not years, since it's a very bad choice of measurements. But those are things you need to decide on. Okay, you can't go down all the way down to the millisecond when they start walking. That's just impossible. Okay, all right. So, ta-da, correct. And why are there 4 different types of programs? This one I didn't even think about asking when I was reading the slides, but this is a very good question. We were only really interested in one effect, right? The special exercising program. Why do we even bother doing this weekly follow-up or just single follow-up? Well, the single follow-up, I guess, is necessary, or else you won't know when the baby starts walking. You in the purple? Sorry? Exactly. So there are many different things that could affect how early the baby is walking, right? If you keep on checking on the parents, maybe the parents will indirectly start being like, okay, my baby really should start walking now, okay? That could affect something. But you can't really tease apart whether it was your visit, your just pure attention that made the parents make the baby walk earlier, or is it your special exercise program that actually mattered, okay? So if you actually do test all these conditions, you can actually test you can tease out the different effects, okay? And these are the planned systematic differences and whatnot, okay? So every time you just say something, just think, where does this go in terms of my vocabulary and whatnot, okay? Let's see, there are 2 treatments. Questions so far? So far, so good? Albert? So the planned systematic differences, so that's the differences that we want to see, that we purposely build into the experiment, so we can say, okay, this group is different from this group because I know I gave them these 2 different treatments. Okay, that's the planned stuff. The unplanned ones are ones that you did not expect or forgot to measure, and then you can't tease out the differences between your condition versus without the condition. And in those cases, that could just ruin the entire interpretation of your experiment, okay? So just for earlier, right? Earlier, my bad experiment was just like, all the parents who want your babies to join a special program, join me, and then that versus me just going to my colleagues and the babies who did not get the training, the unplanned differences are the parents. How active are they, right? I'm not really teasing apart which parents have which kind of babies and whatnot. Okay. Use graphical and numerical summaries to compare the distributions of the responses for different groups of units. So we have time, right? We have time when the baby starts walking. That is what type of variable? The quiz is coming up soon, guys. Come on. What letter does it start with? How about that? So there is a time when the baby starts to learn, right? When the baby is born, hopefully. And then time goes on. So there's a clear initial point, right? Albert, you want to? Oh, no. So there's like the qualitative, quantitative, ratio interval versus ordinal and something else. Yeah. Obviously, I'll fail the quiz, right? So what is it? It's quantitative. Yes, I agree. Okay, good choice. Ratio, yeah, because there's a clear 0 point, right? When the baby is just born, that is a 0 point, so it can't be an interval, okay? Can't be an interval, must be ratio, at least for this class, right? All right, so actually, what would you look at? What summaries would you use, okay? Statistics, again, try to train yourself to ask questions, right? When you're interested in something, what should you ask? How would you explain it to someone, okay? You're not just going to throw all 20 numbers at someone. Or you could, but I don't suggest that. We don't recommend that, okay? There are better ways to actually just pick out the information. So that's why we have these graphical and numerical summaries. Okay? What if I had 100 babies, right? What would you look at? What do you think you might want to look at? Or who wants to know something before we look at anything? What am I interested in again? Nick? How soon the babies walk, right? So there's only really one thing. And I have the 4 different conditions. So let's say, what kind of plot would I want to use? Or chart? The girl next to Nick? A strip chart, box plot, right? Those are all good ideas. And so that will just give you a sense of, for each different category, where are the babies' walking time distributed around, right? And as for numerical summaries, again, we're always interested in where's the center, okay? If I have no concept of when babies start walking, okay? So I'm curious, is it within 10 weeks? Is it within 40 weeks? Within 30 weeks? I have no sense, right? So we need like some kind of measure of the center, roughly where are all the babies centering around, and how spread out is this? Are most babies very, very close to that date, or are they very spread out? Okay? If you're a parent, you'd be kind of concerned about that data, right? Because if your baby's not spot on the average or before the average, you're going to be like, well, how late is too late, right? If the spread of the data, does this make sense when I say the spread of the data? So if I had 100 babies, and the range of the babies who started walking was from, this is me throwing out fake data, from 9 weeks to 40 weeks, okay? And the average, let's say it's 30. Would I be very concerned as a parent if my baby didn't start walking until the 35th week? Would I be concerned? Maybe, maybe not, right? It depends on the spread, right? Again, you're always comparing to the babies, right? So 35, that I know the latest of all these 100 babies is 40, but 35 could be at the lower end, and you're not sure. You might panic. Depends on you, okay? But these are things that you should be caring about. All right. So what to look for in graphs, okay? So again, compare the centers of the distributions. So where are these babies centering around? Okay, where will most of the babies land roughly in terms of their time of walking? Are there any outliers? Okay, are there maybe certain babies are just slower at learning, and then that's why it just takes them longer, no matter what kind of treatment you give them. Maybe there's just parents that are super active in terms of teaching, and that's why no matter what you do, they'll just learn super early. Okay, you could go either way. How spread out are the values for each group? Okay. If your program is very, very good and just makes all the babies learn immediately the moment they can, maybe it's very not spread out. And perhaps you might want to guess maybe the single visit group might have the biggest spread, right? These are things you should start thinking about. Oh, which group do I expect may or may not have a larger spread or a smaller spread? Okay, these are things that you should ask and you should expect before you see the data. And that's why when you see the data, if it confirms your belief, you have an idea. And if it doesn't confirm your belief, that's even more interesting. You should ask, why is this like this? Okay? So remember, ask yourself questions. All right, if the group has different spreads, spreads seem related to the average, consider changing the scale by transforming the data. Okay, so again, if there's like a long right tail, maybe you want to take the log scale instead, and things like that. All right, so here's the data. The 4 different groups, 5 numbers each. And so if I was a lazy statistician, I'd be like, voila, here's the data. Okay? Interpret on your own. Do your job. Okay? I did my job. I collected the data. You know what? Visiting babies, very tiring. 20 of them. Some I visited weekly. Some I didn't. Right? So what do you see already? Or what would you want to see? What do you think? Just glancing at it. Marco? The special exercises seem to be working. Why do you say that? Okay, so they have 2 very low values at 9s. And that's true. weekly report also has a 1.9, but the special exercises seem to congregate around that lower end, right? That 9.9, 10.10. But there's like a slight jump when they go to 13, right? But again, this is only 5 babies. So outliers, maybe, maybe not, right? So yeah, good. And so what types of plots are we going to look at? Strip chart, dot chart, box plot, things like that. And so this is a very key point. When there's not a lot of data, strip chart and dot charts are actually not bad. Okay? When there is a lot of data, density plots tend to be the best. But actually, box and whisker plots, I think, are actually good for both when you have a lot of data or not a lot of data. Okay? Depends on what your lot means. There's quite a range right now in the real world. Okay, so here's an example of the data on a dot chart. So as we can see, can you see my mouse? Can you guys see my mouse? Oh yeah, okay. So yeah, so again, we have these these 2 dots in the special program, right? The 9, 9, 10, 10, and the 13 that's jumping all the way out there. And the regular, where you can see these 3 points just overlapping each other, whatnot. But the 4 different groups are pretty clearly separated. And you can kind of see the centering effect going on. So the single group, notice, is quite symmetric, right? 2 on the left, 2 on the right, middle on this 12, all right? And the weekly group seems to have somewhat this could be an outlier, or it could just have a long left tail, okay? We're not sure. And likewise for the regular exercise group, here we have 3 points. So if you did have a density plot, there should be a hump, and then it should decay off because here are 2 points, and that's like a long right tail instead, okay? But again, this is 5 points. Density plot doesn't really make sense to do that. So let's look at strip chart. This is a different look of the same thing. So if you have overplotting strip charts, did you guys know how to do this stacking? Okay, so it's actually on your section lesson plan. I updated the solutions, and so now they're online on BSpace. It's the same exact file. But just in case you're kind of lazy. Oops, how do I turn this on? Document camera. Always wanted to try this. All right, so for the strip chart function, okay, you'll usually give it the response by the different categories, right? Is that really hard to see? Oh, man. Anybody have a Sharpie I can borrow? I planned to bring one, but I didn't. Okay. Well, here. Really, the only key point is this. There's an argument called method. Oh, thank you. Yes, sweet. Okay, let's see. Is that working? All right, sweet. Thank you. Strip chart, and that's a bracket. Usually you have your response or whatever variable you're interested in seeing, okay, by the different categories. And here's a comma. That's this. And then here in the back, can you even see that? Okay. Usually you would say method equals, okay, and I'm just going to skip down here. You would put in quotes. If you want the chart you just saw, you would write stack. And if you want the chart to jitter around, there's actually an option called jitter, okay? But the best way is always to just do question mark strip chart, okay? It's actually, if you look at the argument methods, they'll just describe a few for you, okay? But here, close that. This is just a different option, okay? You could replace that with this and just see what it does, okay? Questions so far? Right. Okay, this technology is too cool, too fancy. All right, so here's a box plot. And so a box plot actually gives a much clearer view for this particular example, right? So for the strip chart and dot chart, you can kind of roughly see where the data is at, but it's not very clear where the center is. It doesn't really give you the summary of statistics. The box and whisker plots actually gives you a very good sense of where the medians are, whether there's an outlier or not, right? So again, we immediately see that the special group has this one outlier in the left top. The weekly group has this one super baby that's just learning it super fast on its own, okay, just by weekly visits. So those are potential outliers, right? Or it could just be we found some baby at the right tail or left tail of the distribution, okay? And so as we see, the centers, the medians, seem to be in increasing order, right? Special babies walk the fastest, regular, then weekly visits, then single visits, okay? Outliers, the special group and weekly group had 2 outliers. So if there are outliers, what does that alarm you in terms of what summary should I use or what should I think about? What should I ask?
The outliers might influence the mean too much, so you might want to use the median instead.
Exactly. So Tai said if there's an outlier, then the mean may not be a very good measure of the center. So the median is probably much better because it's less sensitive to outliers and it won't move that much, okay? So that's good. And the spread for the special exercise group seems smaller than the others. Is that true? Yeah, so it looks like it, right? The whiskers, if you can see. Ooh, where's my mouse? Yeah, so the whiskers, the overall box itself just seems a bit smaller, which we could see from the data, right? As Marco pointed out, there's like a 9, 9, 10, 10 for the special group. It's very strongly just connected, right? So it seems like this suggests that the special program is working, but it doesn't prove that it's working, okay? Again, a devil's advocate, as what Mike was teaching last time, is that it could be by chance, right? This could just be by chance. The special group, you just happen to draw the 4 lucky babies that were these super babies, right? You never know. And so just summary, the informal analysis indicates that almost all babies who are given special exercise program beginning walking within 9 to 10 months. Okay, so these are in months, not weeks. In comparison, the babies given the other exercise programs have median walk times 1 to 2 months longer and greater spread, okay? So don't always just fixate on the center, the median, or the mean, right? Always think, if you're a parent, you should also care about the spread, okay? Because the spread tells you if this program is very well, all the babies should start around the same time. If the program's not working super well, the babies will still be spread all over the place in terms of their walking time, and maybe it's not as effective, right? Again, what analogy I like to give is if you have a computer manufacturer and they have all types of from super bad computers to super good computers versus another manufacturer that produces computers that are always slightly above average, but that's all their computers are slightly above average. Which manufacturer would you buy your computer from? Okay? Most people usually go for the above average, but very consistent one, right? You just don't want to risk that chance of getting the lower end in terms of the computers they made. So a spread is something that you really should care about, and that's what we care a lot about, okay? There's another slide, so don't worry, just in case you thought it ended. Questions? That's the end of the baby talk, all right? Is it 9 a.m. or am I just that good? No, just kidding. No. Try to process these things, okay? And remember, the main message is ask questions. You should try asking yourself questions. How does this start? Okay. So box models for computing probabilities. I think you're already exposed to box models a little bit. It's actually a very, very powerful idea. Any source of chance or variation, you can basically almost reduce it to just a box, drawing tickets from a box. Okay? The moment you can read, the professors in the stat department are very, very good at that. Okay? No matter what you have, oh, let's think this in terms of a box. Oh, I have this other question. Let's reduce it into a box, okay? Always goes back down to this basic thing. So learn this thing well. And so it just gives us a better sense of like what are probabilities like and how should we deal with them, okay? How should we calculate different things for these random events, okay? So suppose we want to model the flip of a coin 4 times, all right? You toss 2, 3, 4. How would you create a box to represent this, okay? how many tickets would be in the box, what would you write on each ticket, how many draws would you take from the box, and are the draws with or without replacement? Okay? Think about it for 5 seconds. Think about each question. Answer it yourself. Okay, and now those who haven't answered, give me one. Pick one. Pick one and answer one. Nima.
I was going to say I would put, for how many tickets you put in the box, I would put 2.
Okay.
That depends on the other question, the replacement, where I would replace it every time.
Okay. So 2 tickets, right? So if there's only 2 tickets in the box, by the time I flip my second, after I flip my first coin, if I do it without replacement, then there's only 1 ticket left, right? So that means the second toss must be a tail if the first one is a head, or must be a head if the first one is a tail. So it doesn't make sense, right? Because coins don't, it doesn't necessarily have to be a tail if the first one is a head. So that's why draws with replacement make more sense. 2 tickets make sense too, right? There's only 2 different outcomes, head or tail. And there's equal chance. We're assuming a fair coin right now, okay? So therefore 2 tickets make sense. What else? David?
Number 3, I would write heads on 1 ticket, tails on the other.
Yeah, right? So just the different outcomes, heads or tails, right? If you're counting the distribution of people who support Jerry Brown or Meg Whitman, you would just write a box, Jerry Brown or Meg Whitman, right? The number of tickets is, well, how many people support either party or either candidate, all right? Things like that. And the total number of tickets in that case, for the election case, would just be, well, the total number of voters in California, okay? So this box model really extends beyond the coin, okay? It goes much, much further. And what else? How many draws would you take from this box? Again, we're flipping the coin 4 times. That's 4 realizations, okay? We're going to look at this random variable 4 different times, and that's why I should draw 4 different tickets. All right, so 2 tickets, 1 marked head, the other marked tail, draw 4 times with replacement, all good. What are the possible outcomes from the 4 draws? Okay, so what I mean is just that we can have all heads, right? All tails, tail, head, 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 tail, head, 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 tail, head, 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 tail, and so on and so forth, right? There's actually a way of counting all these different outcomes, okay? And it's a beautiful formula, but I don't think we're covering that yet. You may or may not see this, okay? But this is very easy because there's only 4 different outcomes, right? And my question for you is, if I was flipping coins, which outcome's more likely? Adrian? What? Sorry? No, say it. I think you're right. They're all equally likely, right? Why would the 4 coins prefer to have this outcome versus this outcome, right? Each coin, you're just drawing again, flipping again, whatnot, okay? So all the events are equally likely, and that should suggest to you about the probabilities, right? What is the chance that I'll see 4 heads out of 4 coin tosses, okay? Since there's only one possibility for that to happen, the chance of that should be less than these other ones, 3 heads versus 2 heads or 1 head, right? So let's just start thinking, all right? Okay, so it's not as easy to get 4 heads, all right? So how might we adjust the box if our goal was to count the number of heads in a 4 toss of a coin, okay? So previously we had a box, had a ticket named H, had a ticket named T, and we're just drawing. But now I want to count the number of heads, right? So each time I draw a head, it's like I'm drawing what? How would I adjust this box? If I draw a tail, my total sum of number of heads is still 0, okay? That's my first draw. And if I draw a head next time, then my total sum is 1. Draw another tail, that's 1 still. Draw another tail, then overall it'll just still be 1. So how would I adjust my box to reflect this? You? Exactly. Okay? So the tail, you would make it a 1, and a tail you would make it 0, a head you would make it a 1. Okay? So when you draw the tickets and you add up the tickets after the 4 draws, you would have the total number of heads, right? So that's precisely the answer. Okay? And that's exactly how you can calculate other things, like the number of voters who voted for, if you just do a survey, right? And you want to see how many people will vote for either candidate, right? Jerry Brown or Meg Whitman. And then, so you would say, if you're interested in Meg Whitman, then you would say, OK, Meg Whitman is 1, Jerry Brown is 0. Then you start drawing from the pool, right? Ideally, you could have all the voters, and then you could just draw them randomly, right? And they'll all just respond. When they say, I will vote for Meg Whitman, that's a 1. When it's a Jerry Brown, that's a 0, or vice versa, okay? Whichever you like. Okay, and of course, I think there are other candidates, but yeah, for now, let's just keep the model simple, okay? What are the possible outcomes? So what are the possible outcomes for the 4 draws and the possible outcomes for the sum of the 4 draws? That's exactly the same, right? 4 heads, just 4. 0 heads, then that's 0. 3 heads, 3. And then the heads are not all 1s, the tails are all 0s. Questions on how we made the transition? All right. So again, this is just generalizing things further and further, okay? And so here. So now here's your first probability, I guess, a little look. So the chance of something happening is really just the number of possible outcomes interested in over, so the number of ways the event can happen. That's the total number of ways the event that you're interested in, okay? So let's say I'm interested in the chance of 0 heads. So that can only happen in one possible outcome. My total number of outcomes is 16, okay? Therefore, the chance is 1 over 16. And that gives me this 1 over 16 here, okay? So again, if I ask what is the chance I get 2 heads, then there's 6 possible ways I can get a head. They're all equally likely. And since, therefore, if I have 16 events, then that would just be 6 over 16, okay? And that's probability. It's right there, okay? That's it. Just number of interested outcomes over total possible outcomes. And that's it, okay? It, of course, gets a lot more complicated than that, but that is the basic principle, okay? Because if you believe that these are just equally likely, you can just do that. So instead of, again, reading tables and whatnot, what do we like to do? Summarize the data, okay? Make it easier to process. So looking at this now, okay, you can see that this is the probability. So the probabilities, the chance, is the y-axis, okay? The outcomes are the x-axis. So there's only 0, 1, 2, 3, 4, okay? So notice that the middle, there's nothing, just because you can't have a 0.5 number of heads when you're tossing coins. Okay? Very, very difficult. Just lands right there. Okay? So we write it like this. And notice that the middle bar, 2, is the highest. And we're not surprised because we did expect that most of the coins will come from, will have 2 heads. Right? This is, if you toss a lot of coins and whatnot, this is the precise chance right here. Okay? Where is the balancing point? Where is it? Just looking at it. This might be on your quiz, actually. If we just give you a graph. Where's the balancing point? Please draw. So I see people raising 2, okay? Very good choice, right? 2 is in the middle, but that's not just that's not the reason why it's the balancing point. It's mostly because of the symmetry, okay? So notice, when you see a graph, what do you want to look at? How many modes are there? Is it symmetric? Are there long tails, outliers? What's the spread like, right? So the center seems like it's 2. It's symmetric, so the balancing point seems to be the center. Not surprising. The spread is just 0 to 4, and it kind of just decays down, okay? So awesome. So this balancing point is actually called the expected value, okay? So the expected value is this very interesting idea. So how you calculate an expected value is that you take all the possible outcomes. So this is the sum of the 4 coin tosses, okay? So the sum of the 4 coin tosses, there's 0, there's 1, there's 2, 3, and 4. And each one has a corresponding chance of it happening, okay? So the expected value is the sum of that outcome times its probability, okay? And you're summing across all possible outcomes. And therefore, if we just do this calculation using the probabilities we calculated before, you just get 2 exactly. And the expected value will be the balancing point. Okay, that will be true. All right. Anybody still copying this? So far, so good? Questions? Okay. All right. So what if you flip the coin 42 times? Okay. What does the probability distribution look like? What I mean by probability distribution is what is this graph going to look like? Okay. Each possible the distribution of a random variable is all its possible outcomes and the corresponding probability for each outcome. Okay. That is what we mean by a distribution. Okay. Again, all possible outcomes and their corresponding probabilities. That is a distribution. So what would that look like? What do you think it'll look like? Right? Remember, before you plot a graph, think, what should it look like? What might it look? Where's this balancing point? How spread out is it going to be? What are the possible outcomes? Anybody want to try? Albert? The balancing point should be 21 because it's symmetric. Okay, very good guess. What about others? What about the spread? Anyone want to try? Is it still going to look symmetric for sure? Why do you think it's symmetric? Okay? Keep asking questions. Ask yourself, why do I think it's going to be symmetric? Maybe because it's a fair coin, right? I'm equally likely to get a head and a tail, and therefore it just should look symmetric around the center. Why do I think it's 21? Because, again, I expect half heads, half tails. I won't necessarily get it all the time, but that seems like the most likely outcome, right? Okay, so we could try to count all the possibilities, and that is very possible. There's a formula for that. However, we are going to just use R and help us approximate the chances. Okay, so what we can do is, again, 2 tickets, one marked 1, the other marked 0, and we'll draw 42 times. Right? We're tossing the coin 42 times. We're going to, since we're just tossing a coin, again, that's with replacement, since there's only 2 tickets in the box. And so if we try it with R, what we see is something like this. Okay? So this looks pretty nice, right? So what can you point out with me? How does this differ from this? It seems like a trivial question. I know. But these are things that you should start just training yourself. What did I see? What did I not see? Okay? So let's first check the balancing point, right? Seems to be this point, which is between 20 and 22. So 21 seems like the right answer. Okay, fair coin, the middle point. Okay, so the expected value is 21 if you do the calculations. But again, why don't we bother going through the formula for this instance? Is that, well, you can calculate all these formulas, but when you go into the real world, who's going to ask you some question like this, right? Most of the times, the questions will be too complicated in the real life that you might as well just simulate it, okay? And what we mean simulating is that you can pretend that you're tossing the coin that many times, and you can just calculate it. You can look at it roughly, okay? And the actual distribution, when you do the calculation, will look not far off from this at all, okay? But back to my question again. How is this different from this guy? Nima? I think it's not perfectly symmetric. Okay. Yeah, right? 22 is a little bit taller compared to 20. Why would that be? Where did you think this came from? The guy in the far back?
Just because it's equally likely to get heads and tails doesn't mean it's going to be a perfect distribution.
So the distribution itself actually will be, so happening the same amount of frequencies, right? So no, you're on the right idea. So I think the idea that, I don't know your name in the far back, is trying to say is that although I do say I have the chance of 20 and 22 are equally likely to happen, okay? But when I do a simulation, when I actually do run an experiment and I toss 42 coins and whatnot, the chances of 20, the number of 20 heads versus 22 heads, for those to match exactly, that's actually pretty low. Okay? For those to actually match exactly is pretty low. So that difference between 20 and 22 is due to the approximation error. Okay? It's from our randomness of our simulation. Okay? If you do the math, these will look perfectly symmetric. But because we're using an approximation now, it looks slightly off. And that's just due to random chance. Okay? So this is an approximation of the distribution. This is not the distribution itself. But that's a very good observation, right? This is not perfect. What else? Again, we care about the balancing point. What else do I say we care about? Beside the center? The spread, right? Exactly. So the spread is much wider, which you should expect, right? If you do toss more coins, you're more likely to get these far off values, right? If you only toss the coin 4 times, your lowest value can be 0, highest value can be 4. Your spread can't go any further out than that, okay? However, if you do toss the coin 42 times, right, you're ranging from 8 all the way to 32, okay? Is it possible to get 0 heads? It is possible, okay? It's just very, very unlikely. And that's why our approximation here does not even show that, okay? There is a chance, but we just don't have that. So there are actually missing values on the distribution that we're actually not capturing through the simulation. Okay, so just because your simulation should show it doesn't mean it's an impossible event. It just means it's a very, very unlikely event. And that goes back to the last lecture, right, when we're saying when you try to simulate things from a model, when you want to counter-argue the devil's advocate, you're just going to say, well, the event is very unlikely. It doesn't mean that it's impossible. You're just saying it's very unlikely, so therefore we will believe otherwise. Okay? So now I'm going to teach you a little R function. Okay, this beautiful function is called replicate. So I'm just going to skip to the lesson plan tomorrow, since I created it. Okay, so how would I create a fair coin? Can you guys even see this? Okay. So this is actually on your B-space too, just in case you're wondering. Here. Okay. So how do I create a fair coin in R? Okay. Well, remember, it's a box with 2 tickets. So it's just like a vector with 2 tickets, right? Or two elements. 1, 0, 1, 1. That's exactly what you wanted. Okay? And you just paste that in, right? So if we just look at fair coin, voila, 0, 1. How would I draw with replacement? How do I toss this coin now? That is through the sample function. Okay? So sample function, the first argument is the data you're working from. Okay? This is your box. Let me start. I'm just going to talk like this. So the fair coin, the first slot, the first argument is your box. Okay? Whatever your data is coming from. All right? The second argument is the number of draws you're doing. How many are you doing with replacement? How are you doing without replacement? Okay? And then you can add a other argument called replace. If you replace is false, it just means you're not replacing. Okay? You're drawing without replacement. If you're drawing with replacement, then you would say it's true. Okay? So so let's do this. What did I say? Toss outcome equals to this. Okay? And let's look at the first 6 outcomes. So it looks like I got tail, head, tail, head, tail, tail. All right? And so if I said draw this without replacement, that's not even possible, okay? R will give you an error. Because there's only 2 tickets in the box, and you're trying to draw 100 times without replacement. What are they going to do for the third and fourth choice? Okay? So that's that. And then we can just add up these guys to just count how many coins actually happened. So actually, let's try the example in the lecture. Okay? I'm tossing a fair coin 42 times. Okay? And that's just one possible realization. And then, So if I want to calculate the chance of this fair coin, let's see. If I want to calculate the chance, so if I don't know how likely the coin is to land head, maybe it's a biased coin, right? Then I could try to guess it from the data. So I would flip it a number of times. I would take the total number of heads I see, divide by the total number of times I actually tossed it. That's on the right-hand side. And that will give me a guess of what is the chance of landing a head. Okay? And that turns out to be 0.5238095. Okay? But we know for a fact that this coin is fair. So the chance is 50-50. But again, we're only doing 42 tosses, and therefore that's why we're not too surprised that it's a little bit off from 0.5. What if I made this 10,000, right? Then I'd be 10,000. 0.4993, okay? Much closer than before. And this is why some people are very obsessed when you hear about like, oh, but your sample size isn't large enough. Things like that. We can increase one more zero, see how closer it gets. Oops. 99 point. Oh, no. Yeah, this one's right? This one compared to this one on the top. So it's even a little bit closer, but didn't increase that much closer, right? So was it really worth it to get 10 times more samples? Not really, right? We're pretty sure that this thing is probably 0.5. Okay, it's just a little bit off. Again, what I tell my section, I'm not sure what the other section tells you, is like, why do you care? Okay, would you ever care if it's 0.4994 or is it 0.5? Ask that before you do anything else. Okay, when you're like, no, we need more data, things like that. Okay. So how do I repeat this process? Again, to get that whole distribution curve. Right now, what I've done is I only I tossed the coin 42 times. I did it that one time. So that's only one realization. How do I repeat that? So I would say outcome equals to replicate. Okay? Replicate takes in a few arguments. The first argument is, well, how many times do you want to replicate this experiment? Okay, so let's say I want to toss the coin 42 times, and I'm going to do that 10,000 times. Okay, if I want to do it 10,000 times, this is where I would put it. Where else would I put the other stuff is where this. So again, I want to sample from the fair coin. Okay, I want to sample 40. I want to draw it 42 times. And I want to do it with replacement. So let me see if you can see this. Okay. So let's analyze this expression. Every time you look at some code and you're kind of confused, start from the inside. Okay. The inside most function says sample from the fair coin. Okay, this fair coin, toss it 42 times. So it's like drawing from a box of 0, 1, 42 times with replacement. Then I'm adding up the number of heads in there. Okay, and actually, we're not doing probability, so I can just do this. Okay, plot that. And now, I can just look at the histogram of this outcome. Okay, so this outcome is what the probability distribution looks like from our simulation. It does seem a little bit left skewed, right? But that could just be by chance, could not be, right? What if we did it again? What does it look like now? Okay, looks a little bit different or not? A little bit different, right? So again, these are just simulations. And again, we can increase, right? I can make this something ridiculous. This is the beauty of computers. And maybe I added too many zeros there. We'll see. Here, I'm going to kill 1 0. So in R, you can always hit escape to escape out of your thing when you do something stupid like what I did. Let's try just adding 1. And look at this. Okay. So it looks more and more like a bell-shaped curve. And notice that the range is going out now to 5 and 35. Previously, I only got to 10, right? So the really, really unlikely events are now getting picked up. All right, so if I keep on doing it, I might even get a 0 head out of 42 coin tosses. All right, that's it.